Well, thank you all for joining in. My name is Filip Lemic, and the title of my today's talk is Toward Localization in Terahertz-Operating Energy Harvesting Software-Defined Metamaterials Context Analysis. So I will start with the applications and requirements. So with the slide that I shared in my previous presentation, and as I mentioned, we see several application domains, large application domains, and then the idea of the previous talk that I've given was to kind of draw a line between the requirements of different application domains. So interesting thing to see in this talk is that, although in previous talk I talked about in-body communication, body-centric communication, and I've emphasized on the importance of localization in this set of application domains, we started thinking if it is possible, if localization is at all needed in software-defined metamaterials. Why software-defined metamaterials? Well, because it's an interesting and emerging application domain, so that is what drove our interest primarily. As you can see, initially we thought, well, intuitively, there is no need for localization in software-defined metamaterials and metasurfaces. And later on, we kind of changed our mind. And why did we do that? Well, we went to look at some of the applications that are kind of in the domain of software-defined metamaterials and metasurfaces. And people are proposing applications such as, well, network of sensors display smart devices placed on a person's body. So important thing here is person's body. Software-defined metasurfaces embedded into textiles worn on a person. Wireless body sensor networks, again, body sensor networks. Wireless sensor networks in challenging environments, something called auxetics. So these are materials that kind of get more tense under compression and expand under contraction. So it's kind of a natural property of materials. The point of this slide is to show that there is some mobility of software-defined metamaterials, metasurfaces in the applications that they are envisioned to enable. And then kind of the mobility we are talking about here is the mobility, the change between, the relative change between the elements of a metasurface. And per se, this kind of enabling metasurfaces to work even under structural changing is a research direction per se. So you can see a bunch of slides, a bunch of presentations, a bunch of papers that I've taken out of the literature that work on essentially flexible, elastic metasurfaces. The idea there is that the structure of the metasurface is going to change, and we will still want it to be operational under that change. So now to go into the structure or the architecture of a software-defined metasurface. So you have a gateway on the right-hand side in the slide. Gateway is it's a connector to the outside world. And then from the gateway sends information to the routers. Routers distribute this information to a set of controllers, and then controllers communicate, kind of change the electromagnetic behavior of metasurface elements, or take readings from the metasurface elements. And this can be abstracted like communication between sensing and actuating elements and the controllers. So, and focus of this work is really on the network between the controllers and these abstractions of sensors and actuators. And this network can be enabled through wireless. Well, this setup can be enabled through wireless network, right, where you connect controllers by wires to these sensors and actuators. And then there are proposals for wireless solutions, which then brings us to the context of terahertz-based nano communication. Obviously, there are some features of wired and wireless connections. So wired connection allows for reliability, enables for reliable communication. On the other hand, it affects negatively the form factor. In essence, you need wires. For the wireless solution, the point is there are no wires, so you cannot really easily bring energy to the metasurface elements, to the sensors and actuators. What you want to do is you want to have the sensors and actuators and metasurface elements as energy harvesting entities, right? Okay, so what is the intuition? All that being said, what is the intuition for this work? First, we believe the software-defined metamaterials and metasurfaces are going to be flexible. They're going to have the possibility of bending, stretching, rolling, etc. So locations of the metamaterial elements will change respective to one another. And we here make an assumption to an extent. We are not certain what we're saying is correct, but we believe that the location, so the information about the stretch, bend, roll, the changing of the position of the elements respective to one another is going to be important. And we kind of see several potential directions where this could be important. One is, well, localized sensing and actuation. So if you think about traditional wireless sensor networks, the location where the reading from a sensor was taken is important, and it has been a subject of extensive research. So in this sense, for this more novel application, software-defined metamaterials, we believe that localized sensing and actuation could be beneficial. Then there is also the whole domain of research on context-based optimizations in wireless networks, in context also meaning location-based optimization of wireless networks. In that sense, well, you could do the same for software-defined metamaterials and the network enabling control of the software-defined metamaterial elements. Here you can think you have a lot of elements and then you would like to send commands to different elements, but if you use omnidirectional communication, then you're going to interfere with the elements that you don't want to send commands to, right? So what you can do, if you know the location of all the elements, you can use directional communication to kind of target just certain elements, and by doing that you can decrease intuitively interference in the system. Another thing is maybe, well, if you stretch a metasurface until a certain point, it's not going to be operational anymore. So if you can establish that it has been stretched that much, you can say, well, it's not going to work. We have to kind of de-stretch it. And you can do that by knowing the location of the metamaterial element. As I said, these are just assumptions. This is just our intuition. What the idea of this work is to show that localization is possible, because this is currently unclear in the literature. And now if we know that localization is possible or has a high promise to be possible at some point, then we can start thinking, well, what else can we do knowing the location of the software-defined metamaterial elements? And if we know that we can localize the software-defined metamaterials and there is some utility in localizing them, then this can serve as an additional argument for the utilization of wireless inter-metamaterial, the software-defined metasurface communication, in contrast to using wired solution. Okay, hopefully from a previous slide, you know that in this context, we are assuming that the metasurface elements are intermittent, they're energy harvesting nanonodes, so they experience intermittent operations. At a certain point, they can turn off, then they harvest more energy, they turn on, etc. So that is shown on the left-hand side in the slide. Then we are assuming THz-operating, time spread on keying, as a modulation encoding scheme for the communication between the controllers and sensors and actuators, elements of a metasurface. And this is a de facto standard. So as I mentioned previously, pulse is a logical 0, a logical 1, 0, silence is a logical 0 here. In order to enable localization, we're going to take a look at traditional approaches for localization in wireless sensor networks. And there's several potential candidates. One of them is fingerprinting or scene analysis, when you try to match a fingerprint of a location with locations stored in the and the fingerprint stored in the database. Well, you need a training database for that, and we're talking about the nanoscale and the spacing between the nodes so small, and relative mobility and also absolute mobility. So you cannot really generate the training set that is needed for fingerprinting solutions. So fingerprinting is unfortunately not feasible, at least we believe so, for this context. Proximity, the idea of proximity is just to make an estimate if another device is in your proximity, in your range or not. Well, per se, this is not a very accurate localization solution, and here we are aiming at high accuracy of localization. And this leaves us with geometric-based approaches, so some kind of trilateration based of angle of arrivals, trilateration based to time of flight, or receive signal strength. Well, the problem with angle of arrivals is that you either require directional communication or you require some complex signal processing, which you really cannot do because your energy is limited. Receive signal strength is inaccurate. Time of flight requires synchronization between the devices. Luckily, you can do two-way time of flight, where the idea is one device sends a signal, the other device receives a signal, it waits for a certain period, which is known, and then it retransmits the signals based on this two-way transmissions of a signal. You can establish the time of flight measure, and for that you don't need synchronization between the devices. And well, if we are talking about terahertz, terahertz gives us a lot of bandwidth. More bandwidth by nyquist means that we have a better raw resolution. So raw resolution is kind of the error in the estimation of the distance between nodes here. And for terahertz, we get raw resolution of less than 3 centimeters, which is much higher compared to every other technologies usually used for localization purposes. So in that sense, two-way time of flight seems to be promising here. Okay, this is our setup. We have a set of 4 controllers whose locations are known, and then we try to estimate the location of the nano node. On the right-hand side, you can see how we obtain the time of flight. So we send a request from the controller, response back from the node, and then we just estimate the distance between nodes. Well, since you have to think about this whole system as being mobile, right? It's being worn by a person or something like that. So in a sense, what you want to do is you want to localize at a certain point, and you want the system to operate for a certain point, which we call the operational phase. Then it localizes the elements, which is called the localization phase. And this is defined by the location updating period. This is important because it's going to come up in the results. So this is kind of the system that we have. We have a controller. We have a bunch of controllers, 4 of them. We have a set of nano nodes whose location is to be estimated. And we have these 2 operational phases, localization phase, then do whatever you're supposed to do, then another localization phase. And so if we put all that into a flavor of a TeraSim simulator, what we get is, well, okay, the idea of the work is to evaluate different system parameters as a function of accuracy and availability of a localization service. So, well, in the slide, you can see how, as you increase the energy harvesting rate, what happens with the localization errors on the left-hand side, and what happens with the availability of a localization service on the right-hand side, right? So localization errors are given in millimeters and availability in percentages. So you can see, and this is kind of intuitive, that if you harvest more energy per cycle, you get the better availability of your localization service for a certain parameters that we believe they're going to be realistic in practical applications. And as you can see, the average localization accuracy for such a system is on an order of 1/10 of a millimeter, which is fairly accurate. And the direct reason for that is the lot of bandwidth that is available in the terahertz frequencies. So the idea here is the conclusion from these slides, the main conclusion take-home lesson is that we can achieve sub-millimeter level accuracy of this service under a set of well, assumptions and simplifications. But as a first result, it gives you kind of the idea that this is a tangible quest. So these results show energy harvesting rate as a function of localization error and availability, or the opposite. As we can see, we get good accuracy, we get higher availability as we increase the harvesting rate, which is kind of intuitive. On the right-hand side, we can see that our accuracy of the localization service drastically increases as we increase the localization bandwidth. Here we can see as we increase the location update period, as we try to localize the nodes less frequently, well, the accuracy of localization doesn't change, but the availability of the service increases, right? Because we are utilizing it less frequently, so it's available. And the availability comes from the fact that these are intermittent nodes. So if they're not turned on, they will not respond. You will not be able to obtain time of flight, and you will not be able to estimate this node. So this is represented by the availability. And then we have nanonode spacing, which is kind of, you know, what is the distance between neighboring nanonodes. And as you increase this distance, you get lower and lower localization accuracy. And if this distance is really increased to some infeasible level, then you get the availability of 0. But this is something that does not happen for this distances expected in realistic applications. And this is it. So what we believe, we've shown the first results on the feasibility of two-way time-of-flight-based trilateration for localizing Terahertz-operating energy harvesting nanonodes. We have shown sub-millimeter level accuracy and high availability. for system parameters expected in real-life SDM applications. We have quantitatively or qualitatively characterized the effects of various system parameters like bandwidth, like energy harvesting rate, location update period, and we've made several simplifications in this work, so please treat this results as kind of just first insights and qualitative characterizations. So quantitatively things could still change, though we are working on more accurate modeling of the system, and it seems that the accuracy and availability still hold when you increase the complexity of the whole system. And we believe this provides a new argument for the utilization of terahertz-based wireless solutions for controlling SDMs. And this is it. Thank you all for your attention, and if you have some questions, please ask.